So let me say that this time there's going to be some content, as we mathematicians say. Last time was all chat, airy-fairy stuff about what different philosophers have thought. But what I'm aiming to do this lecture is prove the Kochen-Specker paradox, theorem, whatever it is. It's a paradoxical theorem. Let me say it's really quite old. Simon tells me that Ernst Specker, who's from the ETH, they call it, in Zurich, which is the place where Einstein once was, came to Cornell, where Simon was, in the year 1963-64, and that's when they did it, so to speak. And what did they do? There's an operation called, not correctly called, but anyway, called measuring the spin of a spin 1 particle. That's not precise enough. It's called measuring the squared component of spin of a spin 1 particle in a given direction. I'll just call it measuring the spin. And what happens, this is a quantized quantity. It can only take the values 0 and 1. You'll never get another answer from it. I don't know how you want to think of the particle. I think of it as sort of enclosed in a little box, and I point along a given direction to it, and I say, what's your spin in that direction? And it says 1, maybe, or it says 0. How does it actually say it? Well, it says it by being exposed to an electric field. This is rather like, for those physicists who know it, the Stern-Gerlach experiment, where you expose your particle to a magnetic field. But there's a version that was done 5 years later than Stern-Gerlach by a man called Vrede in 1926, which is the same sort of thing with the electric field. The point is really the spin of a spin 1 particle, or rather the component of spin of a spin 1 particle in a given direction, is always 1, -1, or 0. And we don't want that. We want 1 or 0. We identify the 1 and the -1. We can do that by squaring. Is John Vincent here yet? Where is he? Anyway, Kochen noticed this rather curious property that the squared spin, well, first of all, the squared spins in 3 perpendicular directions commute. That's a term that physicists use, which I'm rather against using in this connection, because the definition is, it uses a counterfactual conditional. So let me talk about counterfactual conditionals for a moment. We went to great trouble to remove counterfactual conditionals from our theorem. So what does it mean? Well, to say that 2 measurements A and B commute means that you can do them in either order and you'll get the same answers. So, you make measurement A and you make measurement B. Measurement A might give you the answer alpha, measurement B might give you the answer beta. If you made them in the other order, they'd still give the same answers. Measurement A would now be the second of the 2 to be performed. However, that doesn't mean anything. If I did them in the order A and B, it's no good saying what I would have done if I'd done them in the order, what the answers would have been if I'd done them in the order B then A. And that doesn't matter in cases when there's a well-established theory. If I want to discuss what would happen if I threw a ball up in the air at a speed of, say, 40 feet per second, I don't know whether that's at all reasonable. No, not per second. I could say it would come down and hit the floor precisely so many seconds later and so on, because I know Newton's law of gravitation and the fact that the gravitational constant of the Earth is something or other and so on. So it's only because I have a theory that I know what would have happened if I did something that I didn't in fact do. We're going to prove with the Kochen-Specker paradox that there isn't a theory that explains what the result of this so-called measuring the squared spin of a spin 1 particle in a given direction is. We're going to show that it just can't be done. So it's a misnomer. This thing doesn't exist for all directions. That's the content of the Kochen-Specker theorem. There's a much more famous theorem known as Bell's inequality, which performs many of the same functions as the Kochen-Specker thing. It again shows you that something you thought you were measuring didn't exist before you measured it. It's not good enough to prove the free will theorem. At least I don't believe it is. So we have to... Have we got...
Oh, yes, sir. We have a small problem with the laptop.
This always happens. Anyway, so what... I'll continue for a little bit. The Kochen-Specker theorem, perhaps I'll repeat what I said last time about when I played 20 questions with my sisters, okay, because it's highly relevant here. As I think I told you, if I sensed that my sisters were getting too close to the object I'd selected, I would change the object. And you had to be quite clever to do that. I wasn't always clever enough to deceive my sisters, who were 5 and 10 years older than I was. But if you're sort of really very clever, you can manage to change your object. Well, the particle, the spin 1 particle that I'm talking about, is really very clever. It doesn't have an object in view. So imagine playing 20 questions where you just say, yes, no, for some time. And then only after some considerable number of questions did you give any thought to what the object is. What object you select. You select it after some of the questions. It turns out that that's what the particles are doing. Have we got any hope? Oh, yes. Okay. This is where I wanted to start. By the way, Simon, where was this taken? In Switzerland or? Yeah, in Switzerland, yes. Simon Kochen, looking a bit younger than he does now, but not too much, is on the left there. And Specker, his partner in the Kochen-Specker theorem, is on the right. And Adrian Specker is the little boy in the middle, who's now quite a mature man. Anyway, so that was taken in the 1960s, I presume. Okay, let me continue. What have I got to do? No? Wait a moment. I've got to... Help. I've got to get to the point where... there. Okay, thank you. This is John Vincent, by the way. We have spent a tremendous amount of time preparing the slides here, these later slides. Yeah, okay. Now let me go to the next slide. Okay, so there is what we now call the spin axiom. This is Simon's observation that if you measure, I'm just going to say measurement the spin of a spin 1 particle, but officially you should stick these extra words in 3 perpendicular directions, you always get the answers 1, 0, 1 in some order. Sometimes we call that the spin axiom, sometimes we call it the 101 property. Okay, let me move on. Okay, now there's a Kochen-Specker paradox. This requires a bit of definition. I'll give the definition later, but now let's take this figure. This figure shows 4 cubes. There's a white one, The white one is the only one we'll keep, really. Then there's red, green, and blue. And can you see that the red, green, and blue cubes are got by rotating the white one about the 3 coordinate directions, if you understand me, through 45 degrees. So this makes a rather nice figure. Now, the black dots here indicate certain directions. And what those directions are the symmetry axes of the coloured cubes. I'm not going to call white a colour. They're the symmetry axes of the coloured cubes. So a cube has rotational symmetries about various lines. So let's say, let me move up here. Can we see that arrow there? Is it visible? Yes? So here is a vertex of the red cube. Now, if you join that vertex to the opposite vertex, which you can't see, you get an axis of symmetry of the red cube. If you rotate the cube through a third of a revolution, that's a symmetry. If I take this, now this is the middle point of an edge of either the blue cube or the green cube, whichever you like. And it's a symmetry axis, or rather, again, the line joining it to the opposite middle edge is a symmetry axis of both the green and the blue cubes. This time you rotate it through half a revolution. Where is the other thing? This dot here is a symmetry axis of the green cube. Oh, sorry, it's the end of an axis. I mean, these dots are, or each of them is to be joined to the antipodal dot, the dot that's exactly opposite, and you get the symmetry axis. So altogether, there are 33 lines like this, 33 lines that go right through the center of the cube, and those are the directions. And the assertion is you can't assign ones and zeros to these directions in such a way that the 101 rule is satisfied. I've got to be a bit more precise about that, but that gives you the idea. Let me proceed to the next slide. This is a picture by Moritz Escher, and here is a model at the top of the tower here of the 3 cubes. This model does not have the white cube, that the other ones were obtainable. Here is a dual model of 3 octahedra, and I also have that on my shirt, and it's on the back of the shirt too. It's more clearly visible on the back. This picture, I'm rather fond of Escher. I met him once for 20 minutes. He was staying at the house of Donald Lewis, a mathematician in Ann Arbor. But then later on I learned a lot more about him from his son, George Escher. There was a conference in Halifax, Nova Scotia, I think it was, where George Escher, near where George Escher lives. And it was attended by a lot of people interested in Escher. And one of the interesting things I learned is that these funny plants here are actually some microscopic fungi or whatever it is. And one of the people at the lecture was saying, you know, I'm a mycologist. I teach my students to look at these things here because you'll see here's a rhabdomycia, something ans, you know, and so on. Anyway, that's that. Now I'm going to move to the, going to move to the next slide, if I can get it right. Okay, now, this 101 property is a little bit sort of inconvenient to use as it stands. It's more convenient to split it into these 3 things. So let's say, suppose I've got 3 perpendicular, so remember what it says. If I've got 3 perpendicular directions, they always give the answers 101 in some order. In other words, one of them gives a 0, 2 of them give 1s. Well, you see, I had a teacher who every now and then held his hands up like that to tell us what the right-hand rule was, or this is the left-hand rule, I suppose. Now, this is x, this is y, this is z, say. Minus x is perpendicular to y and z if x is, okay? And if just 2 of x, y, and z are 1s, and the rest is a 0, and just 2 of minus x, y, and z are 1s, then minus x and the others are 0, then minus x must give the same answer as x. It can't change the total number of 1s to replace x by minus x. So opposite directions count as the same for this point of view. They give 1 and the same answer. And then, so I call that rule 1 because it has the word 1 in its description. Rule 2, 2 perpendicular directions cannot both be 0, because if there were, take the third perpendicular direction to those, given any 2 perpendicular directions as a third one, they've got to be 2 1s and a 0, and they won't if 2 of them are already 0. So 2 perpendicular directions cannot both be 0, and then again 3 perpendicular directions cannot all be 1. So that's these rules 2 and 3. I think we'll take rule 1 for granted. It means, you know, opposite directions count as the same. But rules 2 and 3 are the way we'll actually use it. Next slide. Right. Here is our cube marked with these red circles and red lines and squares and so on. Perhaps not terribly clear to you. Let's see if I can rotate it. Yes, I can rotate it. Okay. Now, whenever I show you this cube later on, it will have some black and white spots on it. Okay? And in accordance with rule 1, if anything is marked with a black spot, say, the exactly opposite point will also be marked with a black spot. Okay, well now let's ask what these 3 directions, these are the coordinate directions of the cube. Okay, the lines to the centers of the faces. Let's ask what colors they are. Well, here we are. 2 of them are black. Ah, yes, black means 1 and white means 0. 2 of them are black and 1 is white. I hope that shows up well. Can you see the white spot in particular? Good. Of course, without loss of generality, it might as well be the way I've drawn it. I mean, if you had it like that, you know, I could convert it, well, never mind, I could convert it by rotation into the one I've got here. So we might as well start our colouring like that. What I'm going to show you is that there isn't a way of attaching to these 33 directions blacks and whites in accordance with the 101 rule. Okay. By the way, it doesn't really matter if you don't follow this argument. It really doesn't. As long as you sort of understand vaguely the way it goes. Okay? It goes, well, let's see how it goes. Well, you see, perpendicular to this white spot, all the spots which go around the sort of equator here must be black, because I can't have 2 perpendicular whites. Okay, that's rule 2. So there we are. We've got a lot of black spots going around. And just let's sort of check. Yes, you see, it's okay. I'm going to reset it when I've moved it, because it's very, very confusing if it's not in exactly the orientation I like. By the way, I want to have control over the time. Okay. I can't see that clock up there. I got new specs, but I didn't bring them. Okay. So now, yes. Well, these 2 spots here are opposite each other. They're the ends of a line, a symmetry axis of the cube. And these 2 are the ends of 2 other lines, and altogether those 3 lines are perpendicular. You might not find that immediately obvious. But if you rotate, where are we? We rotate through 45 degrees. These two spots will move along the circular arcs. This white spot will move to here. and the black spot will move to there. And these will move 45 degrees and will arrive at the middle of a face and the opposite. So those three things are perpendicular. Okay, if you don't quite see it, it doesn't matter. They're perpendicular, I'm telling you. And this one has already been coloured black. It was one of the equator of spots that I had before. So that one's already coloured black. So we know that one is black. And so one of these has to be black and one of them's white. Okay? And it doesn't make any difference which we choose. Because if I rotated the cube through half a revolution about, well, let me say it, about this axis here, they would be interchanged. So I might as well suppose it's the way around I've drawn it. And by the way, later on, I'm going to make the same observation that one of this spot down here and this spot up here is black and white, and one is white. And again, it doesn't matter which way around it is. Okay? Okay, so here we are. Let's proceed to the next slide. Well, the next slide shows some of the spots we know. I'm only going to sort of, in these pictures, keep some of the spots alive, so to speak, the ones I happen to be talking about, because otherwise it would be terribly confusing. You'd have all sorts of coloured spots all over the place. And now I want you to notice that these three planes, the planes where the cube hits these blue lines, are perpendicular. Okay, so how did we get that? I rotated the standard three planes, the symmetry planes to the cube, through a certain angle about the vertical here. Okay, and I got this one, which is the equator, stays where it is. It just rotates along itself. This one rotated into this one, and this one rotated into that one. So these three planes are at right angles. Okay. And now that tells me that the lines perpendicular to this point, I hope you're sort of watching here, the lines perpendicular to this one all lie in this equator. And so one of those lines is this line. I say line and I point to a point, but remember I always mean join that point to the opposite point, or join it to the centre of the cube if you like. So anyway, the line joining that point to the centre of the cube is perpendicular to the line joining that point to the centre of the cube. So what colour is this one going to be? Black, because we don't allow two perpendicular whites. Okay, so you followed the arguments, so you're qualified to move on to the next slide. I don't know why that top thing disappeared, it doesn't matter. Okay, now this, oh what a pity, it does matter really. This should be a black point, it just got switched off accidentally. And these are two of three perpendicular lines. There's this line, and this line. And two of them are black. So the other one has to be white. Come on. And there it is. Oh, the black spots come back now. That's fortunate. Okay. So what happens now? Well, so to speak, I'm glad you asked. Oh, you didn't ask, did you? Well, I'm asking for you. This point is perpendicular to this whole plane. Sorry, I'm not drawing it very well, but I think I'm doing better than I would if I used the laser pointer. So that's white. Every spot that's in this plane must be black. Let's do it. There are a few of them. Let's satisfy ourselves that what we've got is antipodal. You see? Here it is. Okay. Well, I said when I first sort of started this business that I was going to switch attention after a time to this diagonal. Well, that's, again, these three spots here, here, and here, the lines joining them to the center are mutually perpendicular. So, well, first, that means that one of these two spots is white and the other black, and I've made an arbitrary decision as to which way it is. And now I just repeat the argument. This whole plane, which is a different one to the plane I was there, is perpendicular to this point. These three blue lines, which are a different set of blue lines going around the cube to what they were before, are mutually perpendicular planes. And now look at it, that spot is has been proved to be black. There it is. That spot's been proved to be black. What's perpendicular to the line joining that spot to the center of the cube? Well, it's this plane. So all of that, so not all of that, I'm sorry. We've got two perpendicular things here, the spot at the top of the cube and this more recently established one. Those are two perpendicular things, so the third member of that trio, which I'm pointing to now, ought to be black. Ah, white. Okay. Now, perpendicular to that white spot is the blue plane that comes out pointing straight towards us. I'm sorry, I can't move this terribly accurately. And so all the spots on that plane must be black. Okay. So last time we had a very similar argument to that, and it ended up proving that these three spots were black. And now we just proved that these three spots are black as well. So let's move. In fact, if we fill in a lot of what we knew, we get all these black spots that I'm showing you. We don't quite get all the white spots. We've seen these white spots. However, look, these three lines are perpendicular. This one here, which I've made rather bigger, or John Vincent made it bigger, to tell you the truth, and this one, those are the ends of three perpendicular lines. And these two, we went through a lot of trouble to prove that those two are black. So this one's white. Okay? That's one thing. But then a very similar argument shows that these lines are perpendicular. One of them is the white line joining that edge of the cube to the opposite edge. And I jumped the gun in saying it was white. And the other two are the lines going to these two spots here. Those are three perpendicular things. Two of them we have proved to be black. And therefore this must be white. Now, can anyone see anything wrong with this picture? Yes. Well, you see the line joining this spot to the center of the cube and the line joining this other spot to the center of the cube, they're perpendicular and they're both white. That is a contradiction. Well, I'm sure most of you have forgotten what on earth this was all about. I mean, it's quite intensive following these arguments. We've been trying to solve a puzzle, okay? And the puzzle is to assign zeros and ones, which I've been symbolizing by white spots and black spots, to the various directions. Not to all the directions of the cube, but to these 33 directions in such a way as to satisfy the 101 law. And you can't do it. Okay. You can't do it. So what does that imply? Well, we didn't have to do it. But we would have to have done it if the particle, how can I say it, was constrained not to cheat at our game of so many questions, 33 questions I suppose it is, if it was constrained not to cheat, if it wasn't allowed to change its mind. So in other words, what I'm saying is, well, in technical language, there isn't a function defined on the space of directions, of all directions. There isn't even a function defined on these very 33 particular directions that satisfies the 101 law. So, nevertheless, spin 1 particles behave this way. So, what happens? Well, there's a lot of sort of slightly nonsensical talk about this, particularly in popular physics books, which don't always discuss this experiment, but in similar experiments. It's often said, well, for instance, one of the standard things is, it's often said that the position of a particle and its momentum, and if we know the mass of the particle already, the momentum can be replaced by the velocity, are sort of incompatible quantities. This is Heisenberg's uncertainty principle. It's often said, if you measure the position very precisely, you disturb the particle. And so its velocity is no longer known. Or if you know the velocity very precisely, you've again disturbed the position. That's not an accurate way of talking. It sort of presupposes that the particle has a position and a momentum. And there are many similar examples of so-called conjugate quantities or something, which are like this. You can't simultaneously assign values to two conjugate quantities. In this case, we can't, it's a rather more subtle situation, we can't assign spins, that is to say squared components of spins, to the particle. There is no way of doing it. It's not a question that the measurement in one direction disturbs the answer it was going to give for another direction. Oh dear me, no. A consistent set of answers doesn't exist. That's a really big deal. And it's important to realize what goes on, you know. What does it mean? Does there exist? Well, maybe there does. I don't know. What am I trying to say? This is the 40-year-old version of what we've now called the free will theorem. So let me try and say the respect in which it differs from the modern version, which is only 4 years old. I mean, this already suggests, and in fact, the philosopher Robert Nozick sort of thought it proved, that, how can I say it? Well, he thought it proved that Leibniz's principle of sufficient reason was false. You will remember Leibniz's principle of sufficient reason, I hope. Nothing ever happens, says Leibniz, without there being a sufficient reason why the thing happens and not something else happens. Okay? We'll strengthen this so that it really does disprove Leibniz's principle of sufficient reason. We'll show eventually that not only doesn't... You see, what this shows is there doesn't exist a function of direction which tells you what the spin is. Until you make the measurement, just not there. And in the way I think of it, the particle answers you on the fly. It just gives an answer. And if you ask it about its spin in three orthogonal directions, it gives answers which are consistent with the 101 rule. But if you ever ask it about one direction and then about another direction that's not parallel or perpendicular to the one you first thought of, all bets are off. It no longer has any promises to live up to. In the standard slang, measurements that aren't in perpendicular or parallel directions don't commute. But we see that doesn't mean that if you measured them in the other direction, in the other order, you'd get a different answer. Because there's no saying what the answer would be. There isn't an answer in mind. It takes a long time to absorb that. You know, the particle makes up its mind and tells you the answer on the spur of the moment. It doesn't have an answer in mind, really. That's an anthropomorphic way of talking. Let me see again what the time is over here. Oops. Oh, curses, I've got some... Okay. So how are we going to strengthen this when we prove the free will theorem? Well, what we're going to do is show that, in fact, let me discuss a way in which it could be false. It could be that what the particle tells you is not just a function of direction. It doesn't depend only on the direction. It might depend, it might depend on anything, mightn't it? It might depend on the order in which you ask the questions. It might really be, if you ask about this direction first and then this direction, you get a different pair of answers to if you ask them in the order. It might be that it depends what day of the week it is. It might be that the particle has been listening to your conversations with your fellow physicists, and if you mention the magic word abracadabra, it will give you one answer, and if you don't, it will give you another answer. It might depend on anything in the past history of the universe, or should we say in that part of the universe which is in the past of the experiment. Now, in fact, the free will theorem says no, it doesn't depend on all of that. It says there's no function, not just of a single direction, but of directions that you're going to ask the particle about, and everything in the past history of the universe up to the time you make the experiment. And we can only prove that by contradiction again. We've just given a proof by contradiction. We supposed there was a function of direction, and then showed that it couldn't be defined on all those 33 special directions. Well, now we've got to do a much more sort of complicated thing. We've got to suppose there is a function not only of directions, but of the past history of the universe. Everything in the universe that's ever happened before it. And then we've got to deduce a contradiction from that. Okay? Now that's what we've done. It's not entirely trivial. It's not hard. But it's not trivial, and it's got a certain amount of subtlety to it. So now what am I going to say? It depends on a few things that we sort of saw in the first lecture, or at least I mentioned in the first lecture. You've seen the axiom called spin. Okay. It depends on another principle, which is weakly stated as information can't travel faster than the speed of light. All that's important to us is it can't travel faster than a finite speed. So we call that fin. Fin abbreviating finite. However, how can I say it? The spin axiom, I don't want you to take anything on trust. Well, I do actually, but I want you to sort of consider the following thing. Suppose you don't believe in the spin axiom, and also suppose I'm not a physicist. I'm a physicist, which is not true, but suppose I were a physicist with a very well-equipped laboratory. You don't believe in the spin axiom, so what do you do? I sort of say, well, look, do this thing called measuring the spin of a spin-1 particle in 3 orthogonal directions. You choose the directions, and you adjust the equipment so that it points in 3 directions, one after another, or all at once, actually. And you get 2 1s and a 0. Okay? Do it again with a different particle. You get 2 1s and a 0. Repeat this sort of experiment thousands of times. Well, probably one of them won't give 2 1s and a 0. Well, we say that's experimental error or something. But that's what I mean, anyway, to say that this is operationally decidable. Okay? It's a prediction of quantum mechanics, but we're not supposing quantum mechanics, not in principle. We are just supposing a particular very small consequence of quantum mechanics, and that consequence is, in principle, operationally testable. That's a very important thing from this, from our point of view. Okay, now we have another axiom, and this axiom is rather strange. It says, called the twin axiom. You can put two spin-1 particles into what's called a singleton state, and then separate them by a large distance, so large that light would take 5 minutes to travel from one to the other. And in accordance with the Finn axiom, if you now do two experiments with a time difference of significantly less than 5 minutes, say 1 minute, they can't signal to each other. Okay. Okay. Anyway, that's the twin axiom. It says that you can put them into the singleton state, and then, as it were, they promise to give the same answers if you ask them the same questions. So I ask this one in this direction, and I get a 1. Then, even though this thing is very, very far away, I know that if my colleague has asked it the same question in the same direction, it will also give a 1. It will work if he's asked that question 1 minute ago, if he's asking it now, or if he's asking it 1 minute in the future. It doesn't matter. In fact, there's no difference between those concepts. So that is this famous thing that Einstein wrote to the New York Times about in May 1935, I think it was. The New York Times, well, actually Einstein wrote to the New York Times very annoyed. The New York Times published an article saying that Professor Einstein was going to exhibit an argument that proved, roughly speaking, that quantum mechanics was nonsense. Einstein wrote furiously the next day to say that his colleague had inadvertently let the cat out of the bag. It was only to be announced at the next meeting of the American Physical Society. It's known as the EPR effect, Einstein, Podolsky, Rosen. Fine. Suppose you don't believe the twin axiom. The same is in principle true, okay, but only in principle. I take you into the lab, do the thing called putting the two particles into the singleton state, separate them, and I let you and your colleague perhaps examine them, ask them the same questions, if you like, and do it thousands of times and see if you all get the same answer. Those are two. I'm not really relying on that. These are only thought experiments at the moment, because, in fact, those experiments are terribly difficult. Some approximations to them have been done, the distance of separation being only 22 kilometers, but we'd need them at interplanetary distances, because it's important that you're free to make a free will decision in between the two experiments. So, and free will decisions, the physiologists tell us, take about 1/10 of a second. In 1/10 of a second, light can travel really rather a large distance, 80,000 miles, which is more than the radius of the Earth. It's not more than the distance between the Earth and Mars. The distance between the Earth and Mars is always at least 5 minutes. And that's plenty of time. So we think of our two experiments as being performed on Mars and on Earth. Well, you can't do that yet. It's very difficult to imagine when you'll be able to do it. But nonetheless, quantum mechanics is one of the most stringently tested of all physical theories, and I don't really have any doubt that it will pass this test. It's not wise to bet against quantum mechanics, okay? Its predictions are a little bit hard to understand and so on, but they've always been true. What am I going to say if this one turns out not to be true in sometime? Well, I'll probably be dead before I have to say, but well, I'll just say sorry. The thing is, I don't apologize for believing this. It's not sensible to disbelieve a prediction of quantum mechanics in advance of the evidence. It's not sensible either to absolutely believe it, but you believe it with very high probability. And, you know, as soon as this is disproved, well, that'll be a Nobel Prize, obviously. I mean, it's a very big thing. So this is tentative still, but not very, okay? You'd be unwise to bet against it. But I want to say something now about Finn, because I sort of played great stress on the fact that twin and spin were operationally testable, okay? Which is good because they're the weird ones. They are the ones that depend on quantum mechanics. Finn is much more tame. It would seem that there's little doubt about it. It's just a consequence of relativity theory. And, you know, relativity theory has been very well understood for a lot of time. There's no problem in comprehending it. However, Finn says there's a finite upper bound to the speed with which information can be transmitted. How can you possibly test that? We don't know all ways of transmitting information. It might be possible to transmit information by, say, ESP. And I don't believe it for one moment. I think the people who do believe it are rather flaky. But it might be possible. How can I disprove that? You know, not at all. It's important to realize that Finn doesn't have the same clarity of statements as the other ones. It mentions all possible modes of transmission of information. Well, there's a better reason for believing it than that it's operationally testable. That better reason is Finn follows from the theory of relativity, and the theory of relativity is really a symmetry principle. It says that the laws of physics are invariant under certain symmetries. If you travel at a uniform speed in some direction, you observe the same physics as I do when I stay at home. What's funny about that is that there's another assertion that goes with that the speed of light is independent of the observer. So, I mean, if I shoot a beam of light along there, and then I start walking after it at, say, 3 miles an hour, its speed ought to be less with respect to me than it was with respect to this desk, say. But it's not. And that's a sort of statement that seemed very paradoxical when Einstein stated it. Now, what I'm going to do next lecture is give a sort of easy introduction to relativity theory, which has no formulae in it whatsoever. You can follow it. You really can follow it. And it shows that the so-called paradoxes of relativity theory, well, they're only paradoxes because they surprise us. They conflict with the opinions we probably grew up with originally. They are perfectly consistent and perfectly natural when you find the right way of looking at them. So that's important, because what happens is, if you could transmit information faster than the speed of light, then with respect to another coordinate frame, another frame of reference, you could actually transmit information backwards in time. And that's sort of nonsense. You could change the past, okay? Now what happens is, it's hard to explain it. Do I have to? This phone did. I think I sort of finished there. I mean, no, I finished a bit early. I'm sorry, I don't have to. But so what I'm going to do then is show that. Well, for instance, I don't know. Have you heard of the twin paradox? Many of you. Some of you will have. What relativity says is that one of the consequences of relativity is that if we have two twins, one of them stays at home and the other one makes a journey going very close to the speed of light in one direction, and then he returns. That's again very close to the speed of light, but in the other direction. Then the twin who stayed at home ages by more than the twin who went apart. It seems a very peculiar thing. There was a famous physicist, Herbert Dinkel, who really never got over this thing. He got lots and lots of papers about the twin paradox. It seems as though the symmetry, at first sight, between the twin who stays at home and the twin who travels. After all, if you take a coordinate frame for the twin who travels, the twin who actually stays at home appears to move away, and then after a time turns around and moves back. But there isn't, because the twin who travels actually experiences a physical effect, this enormous acceleration, or perhaps I should say deceleration, when he turns the corner and decides to come back. There isn't symmetry at all. You might think you'd never understand the twin paradox, okay? But, you know, when I talked to an audience rather like this 10 years ago, everybody understood it, I think. Well, I don't honestly now. I asked them, they seemed to think they understood it. Maybe they didn't really, but anyway, it's easy to understand, the twin paradox. Yes, well, that's nothing to do with our twin axiom. I've got to now show this consequence of relativity first, that you can't transmit information from faster than the speed of light. And that makes this EPR thing really a paradox. And I'm going to discuss EPR in the lecture after that. I've decided that the sixth lecture, is too long. I mean, there's too much material to go in it. And so what I've decided to do is to cut short a little bit of material in the fourth and fifth lectures and import material from the sixth. The sixth is about the philosophical consequences and the scientific consequences of our free will theorem. It's got both. I firmly believe that particles all about us in these chairs and so on are taking free will decisions. They're just deciding to do something for no reason. Leibniz's principle of sufficient reason is false. Of course, in fact, you know, there are 10 to the 29 or something particles in this chair. Some of them are suddenly deciding to move upwards for no reason. About as many are deciding to move downwards for no reason. It all cancels each other out. The chair doesn't sensibly appear to move. I think this is a bit more contentious, that somewhere inside us, probably in this region, there's a way in which this cancellation is avoided. And so from the free will of particles, which I'll show you really happens, we get our own free will. But as I say, that's a bit contentious. Let's give up.